Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 16 physics series, where I am trying to help you to achieve 60 marks in upcoming 2025 KCET physics exam. So if you are following us, you should know that we are going through each and every chapter, and every Sunday we are conducting KPL. So tell me how much you scored in last week's KPL, that is KPL 7. Also, how was your Dashera? Don't forget to mention that in the comment below. Today I will start with a new chapter, Nuclei. Okay, and in the part 1 of the chapter we are going to discuss mainly about nucleus, structure of nucleus, okay, and nuclear binding energy mainly. Okay, so everything about nucleus and nuclear binding energy we are going to discuss in today's lecture. Also, one more important thing is that in this chapter there are most of the previous year questions are now out of syllabus, because one important concept, radioactivity, is now only one paragraph long. It was used to be a very long part of the chapter, core of the chapter. Now that is completely removed, so I will not be doing a full length previous year questions for this chapter. What I will do, whatever leftover question is there, I will discuss during the lecture, as I do always, and if some questions are left, I will discuss tomorrow during part 2. While doing part 2, I will also take up all the previous year questions at the end of the discussion, so be ready for that. So this will be only 2-part video where everything will be covered, including the concept of the chapter and the PYQs, okay, because most of the PYQs, if I look into them, they are not part of the syllabus. I will show you one example tomorrow that what all are not part of the syllabus, that you don't need to study. Okay, but there are few questions we are like in previous year questions, maybe 5 to 10 questions are there, whereas at least one question every year was coming from that concept. Radioactivity, radioactive decay, etc. are no longer part of the syllabus. It was there in 2024 JEE syllabus, so if you are preparing for JEE, be careful that radioactivity may still be there in your JEE syllabus, but it is not there in KCET. Last year some questions obviously came from that part, but that was later decided it is no longer part of the syllabus, so they removed those questions, they deleted those questions. They are not considered for while considering your final rank. So now I can guarantee that this radioactivity related questions will no longer be there in your KCET 2025 exam. In case they are there, you can ignore that. They will be either deleted or given as a bonus question. Okay, so now if you have not yet joined our WhatsApp channel, you can join the WhatsApp channel where we are sharing the question paper every week for KPL exam, right? So you can check the link given in the description below. There you can check all the question papers previously shared, and also whatever questions that we are going to share in future every Sunday, absolutely free of cost. KPL, don't forget to join. So let's start with the chapter. So before we start, we will look into the table of contents as usual. Okay, what we are going to discuss today, first of all we will discuss what is nuclei. We have learned briefly about nuclei in our previous chapter, where we were discussing about atoms, structure of atoms. Now we will also discuss atomic mass, because now we are discussing small particles, so it is very important to know about atomic mass. Okay, why it is important. Next we will discuss about discovery of neutron, one of the biggest historical achievement of human history of recent times. Then we will discuss about composition of nucleus, how what all are the main part of the nucleus. Then we will discuss size of the nucleus, another important concept, and then we will discuss nuclear binding energy. This is very important. Okay, nuclear binding energy is also very important. Now let's look into the first part, nuclei. Okay, experiments on scattering of alpha particles demonstrated that the radius of nucleus was smaller than the radius of an atom by factor of about 10 to the power of 4. So we have seen during alpha particle scattering that the most part of the atom is empty, right? And most of the mass of the atom is concentrated at a very tiny center. That center was called nucleus, and the credit of discovering nucleus goes to Rutherford because he is the first person who did that experiment, right? We have already discussed that. Now nucleus was smaller than the radius of atom by the factor of 10 to the power of 4. So what is the meaning of that? That nucleus is very, very small. Okay, so nucleus is very, very small. What else? This means that the volume of nucleus is 10 to the power of minus 12 times the volume of the atom. So we have learned that the radius in terms of radius of the atom, suppose radius of the atom say r, then radius of the nucleus is 10 to the power of 4 times less. Okay, so suppose radius of the atom is r atom, okay, and radius of the nucleus is r n, okay, r nucleus. R nucleus, then r atom divided by r nucleus is basically 10 to the power of 4. So atom is much bigger than that of the radius of the nucleus. Now in terms of volume, we know that this is a spherical size, so volume is 4/3 pi r cube, right? Whatever if you find the volume of the atom, it will be 10 to the power of 12 times more than that of the nucleus. So nucleus will be 10 to the power of minus 12 less than that of the atom. In other words, atom is almost empty, right? So atom is almost empty and nucleus is very tiny. If an atom is enlarged to the size of the classroom, the nucleus would be of the size of a pinhead. What is the meaning of that? If you use board pin to stick notices in your college, right? You have seen, or some pins in your home to pin something on your wall, right? If you increase the size of the atom, and if you compare that, okay, entire atom is located in that classroom, okay, entire classroom is the atom, then that pinhead, or you say head of the ballpoint pen, okay, that will be the size of the nucleus. So nucleus is very small. Okay, you may have seen in some animations or videos that they are showing the nucleus too big, but actually in reality nucleus is very small. Okay, so nucleus is very small, but entire mass of the atom is located in that small volume only. Okay, now let us solve one question. This is a very generic question from your previous year questions. So as I said, I will complete all the previous year questions while doing this chapter itself. Also the homework questions are from previous year questions, so you have to solve them as well. Now 2 protons are kept at a separation of 10 nanometers. Let Fn and Fe be the nuclear force and the electromagnetic force between them. So Fn is the nuclear force and Fe is the electromagnetic force or electric force. Okay. Then which one will be greater, which one will be smaller? So first of all, let us understand the concept of nuclear force and electric force. I have discussed that while discussing the chapter electric charges, that electric force is very weak compared to the nuclear force. Nuclear force is the strongest force in nature. Okay, nuclear force is the strongest force in the nature, and gravitational force is the weakest force in the nature. So obviously electric force is less than that of nuclear force, so correct option is option A. Okay, so they have mentioned Fe and Fn differs only slightly. No, that is not correct. They differ hugely, and electromagnetic force or electric force, basically electric force, because they are static. So if they are static, then only electric force will be acting. If they are moving, then electromagnetic force will be acting. I hope you are clear about that. These are the very conceptual concepts. So only option is electric force is weaker than nuclear force. Now let's look into another new concept called atomic mass. Okay, so what is the atomic mass unit? Mass of an atom is very, very small, right? So basically we have realized that atom is very small, mass of the atom will be very, very small. So if you try to represent them in terms of our known SI unit, that is kilograms, or our common unit, say grams, then it will be super small, right? It will be super small. So for example, if you remember, in case of electron, we say the charge of an electron is 1.6 times 10 to the power of minus 19 coulomb, right? So that's why we don't use that as a fundamental unit of charge. We use coulomb as a unit of charge, right? Even though the fundamental unit, which is the charge of an electron, is very small, we generally do not say charge of an this is a 1 electron charge, 2 electron charge, or 10 to the power 20 electron charge. We do not mention that. We mention this in terms of coulomb only, right? Even though the charge of an electron is very small, that's why. But when we are mentioning the charge of a small objects, okay, smaller charges, then we mention it in terms of electronic charges, right? So 1e, 2e, 3, like that. Similarly, in case of mass also, atom is very small and its mass will be obviously smaller. So to express the mass of express the atomic masses, okay, we need a new unit. We needed a new unit to express the atomic masses, right? This unit is the atomic mass unit, small u. Previously it used to be denoted by AMU, but now it is only denoted using U. Okay, defined as, it has a definition, obviously it has a defined as 1/12 of the mass of the carbon 12 atom, C12 atom. According to this definition, 1U equals to mass of one carbon atom is 1.992647 times 10 to the power of minus 26 kg. So you can see that it is a very, very small mass divided by 12. Okay, so 1/12. Why 1/12? Because carbon has 12 ingredients inside it. So we will see all the ingredients inside a nucleus very soon. But carbon has 12 mass number. So they have divided it by the mass number, and it comes out to be 1.66 times 10 to the power of minus 27 kilogram, almost, approximately. Okay, you can take this value as approximated value. Okay, now the atomic mass of various elements expressed in atomic mass units U are close to being an integral multiple. So for an atom, if I say an atom, single atom, for a single atom the atomic mass unit is a integer quantity. But when you say the mass of an element, so what is the difference between single atom and element? When you are saying element, say hydrogen element or oxygen element, in that case what you have to do, you have to calculate the entire oxygen family. Total oxygen family divided by number of oxygen atom is there. There is a process. I hope you have learned that in chemistry, how you can find the atomic mass of different elements. Okay, but for a single atom it is a integer quantity. But however, many striking exceptions to this rule. For example, the atomic mass of chlorine atom is 35.46. This is the average value. Okay, this is the average value. You have to take the average for any arbitrary element. If you say the atomic mass of that element, in that case you are representing the entire chlorine family. Okay, individually the mass of say one chlorine will be different than that of other chlorine, but when you are averaging that, you have to say, okay, the average atomic mass of chlorine is 35.46. we cannot represent individual atoms, so that is the representation of the entire chlorine family. That's why we represented it using 35.46 U. Okay, so this is the common thing. There used to be question coming from this, even though atomic mass number is a integer quantity, why atomic mass is a fraction? Okay, there are different kind of question. I hope you have answered those questions in your chemistry. Very famous question from the chapter periodic table as well. Now, mass of a proton, very important. Mass of a proton is 1.007 U. Okay, 727 U. Okay, but you can write this as 1.007 is closest number. Okay, mostly it is given at the beginning of the exam. if it is not given, you can assume 1.007 for proton. We will see for neutron as well. Okay, and it is equals to, if you can see, 1.67262 to the power 10 to the power minus 27 kilogram. Okay, so this is a very small number, but when you are saying mass of a proton, you can see this is not very small, it is 1.727. 1.0072, so almost 1, but you cannot ignore, because this is a very small unit, you cannot ignore even this small mass. Okay, we will see that why in a while. Mass of a single electron is another much smaller number, 0.00055 U. Okay, 0.00055 U. Okay, so 0.00055 U. So electron is much smaller, much lighter compared to that of proton. Okay, proton is much higher than that of electron. When we say atomic mass, a mass of an atom, generally we only consider proton and neutron. We ignore electron completely because electron has very small contribution towards it. Okay, now isotopes of hydrogen. What is the meaning of isotope? I hope you know what is the meaning of isotope. Isotope means when there are different weights of single element is present in nature. Okay, so different weights of single element is present in nature. They have all chemically they are same, their chemical properties are same, but they have different masses. Okay, if their mass is different but number of electrons in the outer shell is same, then they are called isotopes. Okay, so hydrogen has 3 isotopes, right? What are those? So even though we have not learned the symbols yet, so we can write this as 1H1, 1H2 and 1H3, right? So if you remember, this is the symbol for hydrogen isotopes, right? Okay, we will learn about this symbol very soon. Okay, the normal hydrogen, obviously the hydrogen which is we say our normal hydrogen, that is, this is normal hydrogen. Okay, available in nature, most abundant. Then deuterium. Okay, deuterium is little bit less abundant, and it has lot of uses as well. Deuterium has lot of uses. And second is tritium. Now tritium is something which is not naturally occurring. Okay, tritium is only produced in labs, and it has a very small lifespan. It decays very fast to give you a normal hydrogen. Okay, so tritium is not naturally occurring. You should remember that it is only available inside a lab. Okay, now discovery of neutron. Okay, since the nuclei of deuterium and tritium are isotopes of hydrogen, they must contain only 1 proton each. So why is so? Because hydrogen has how many electrons? Hydrogen has only 1 electron. So 1 electron means what? At the first chapter, electric charges, we know that elements are by default neutral in nature. They do not give us shock. We don't get shock if I touch anything. For example, hydrogens are present. Hydrogen is present in our air also, maybe in small quantity. Okay, but if we touch, we do not get any electric shock. Even all the air molecules present here, they do not give us shock. If I touch this board, I don't get shocked. Why? Because even though they have electrons and electrons present, they have equal number of protons present as well. So these protons do not give us any shock. Okay, because electrons and protons, they balance each other. So total number of charges inside an element should be 0. Right, so total number of charges should be 0. That means deuterium and tritium, they are all isotopes of hydrogen. They have only 1 electron. So that means they should have only 1 proton. Okay, so that means why they have different masses. Why their masses are different. Okay. So, but the masses of these nuclei of hydrogen, deuterium and tritium, are in the ratio of 1:2:3. So, very surprisingly, mass of hydrogen is, if you take 1, then deuterium is 2, tritium is 3. So, same element having different masses. How is this possible? Okay, this is not something to joke about. So this is what scientists stumbled, and they thought, okay, there may be some other particle involved in, okay, that we do not know yet. Okay, therefore the nuclei of deuterium and tritium must contain, in addition to a proton, some neutral matter, right? Some neutral matter must be present inside the hydrogen. So that is why deuterium has mass 2 and tritium has mass 3, right? So that's what they decided. Now how can we detect that? Now it is, you should remember that any charged particle, for example electron, it is easy to detect because it is a charge, right? It will be repelled by another similar charge. Okay, similarly proton is also charged, even though it is located inside nucleus. You can detect it because it has some charge. You can, if you somehow able to split one nucleus, and if a proton comes out, you can repel it using another positively charged object, or you can attract it using electrons, right? So based on that you can determine, okay, there are some positively charged particle present, and you named them as proton. Electrons was discovered by Thomson, right? Now neutron on the other hand, that we are going to discuss, they are neutral in nature. Now neutral objects, they do not get attracted or do not get repelled by any external field. So that is why it was very difficult to determine the presence of this neutral particle, and only few years in terms of history of science, okay, history of science, after discovery of electron, within 10 years protons was discovered, but neutron took much longer than that. Okay, after discovery of electron, neutron took almost 40 years to be discovered. Okay, now the amount of neutral matter present in the nuclei of these isotopes, expressed in units of mass of proton, is approximately equal to 1 and 2 respectively. So what is the meaning of that? If you consider the mass of proton to be 1, okay, mass of proton to be 1, for normal hydrogen mass was found to be 1. For deuterium, the mass of proton, 1 mass of proton. For deuterium it is found to be 2 mass of proton, and for tritium it is 3 mass of proton, right? So these are the common observation that we have observed. Now if so, it is very close to this value, so that means something is hidden inside that nucleus, which is almost of equal mass that of proton, right? Almost of equal mass that of proton. Okay, the amount of neutral matter present in the nuclei of these isotopes, expressed in the unit of mass of proton, is approximately equal to 1 and 2 respectively. So this fact indicates that the nuclei of atoms contain, in addition to protons, neutral matter in multiples of a basic unit, right? So basic unit, we calling it U. This hypothesis was verified in 1932. So if you remember the discovery of electron, it is almost 40 years. After 40 years, James Chadwick, who discovered a new particle, and he named it neutron. Why neutron? Neutron stands for neutral particle. Okay, in fact James Chadwick won Nobel Prize for discovering this particle, neutral particle. It was very difficult to discover. Okay, neutron was the last particle of the family which was discovered. There are some subatomic particles as well, but to make a nucleus working, only proton and neutrons are required. To make an atom whole, electron, proton and neutron are required. There are some subatomic particles, they have a different science, branch of science, okay, where we are discussing subatomic particles, etc., nuclear physics, but for now electron, proton and neutron are sufficient for an atom to exist independently. Okay, now there are few properties of this, we will discuss about that. The mass of the neutron is given by 1.00878866 U. Okay, so if you remember, mass of proton was about 1.00727 U. Okay, and mass of neutron is 1.00866 U. Okay, if you don't remember these values, at least you have to remember up to these values. Okay, 0.007 and 0.008. Okay, 0.007 for proton, 0.008 for neutron. Okay, one is common. So this is at least you have to remember, even if you don't remember the decimals. And in fact, if you approximately remember these values and use these values, you will get the correct answer. Okay, don't worry about it. Okay, now composition of nucleus. Another important concept, the positive charge in the nucleus is that of the proton. So what all are part of the nucleus? Positive part charges, that is given by protons. Okay, proton carries 1 unit of fundamental unit, 1 U, almost 1 U, right, 1.007 U. Okay, 1 unit of fundamental charge and is stable. Okay, so fundamental charge is electron. So proton carries 1 unit of fundamental charge and it is positive and it is stable. Very important to know that a proton is a stable particle. If it was not stable, then we would not have been even existed in this universe. Okay, so universe would have been still been a form of gas, because nothing was stable. It created in a big bang and it destroyed immediately after creation. Okay, because it was not stable. But electron is stable, proton is stable. Okay, but neutrons are not. We will see that. Okay, neutrons are neutral but not stable. Okay, neutrons are not stable. It decays. Okay, what is the decay? A neutron decays into a proton, an electron and an antineutrino. So it is a very new particle. Okay, we will not discuss too much about it. If you have any interest, you can go and check in the Wikipedia or any other online platform. Okay, it was previously it was part of the syllabus. Now no longer it is part of the syllabus. It is little difficult, obviously, that's why it is no longer part of the syllabus, but you can discuss, you can check that in the online resources. So electron is stable, proton is stable, but neutrons are not. Okay, neutron decays into one proton, okay, which is plus one electron, which is negative, plus one antineutrino, and neutrino is denoted like this, I think, nu naught. Okay, so this is the basic decay of neutron. So neutron generally don't stay stable, don't stay neutral outside nucleus. Neutrons only exist inside the nucleus. Okay, inside the nucleus only neutrons are there. Outside neutron, as soon as you take it out of the nucleus, it will decay and it will give you these particles. Okay, so that's why, because of this, you see the neutrons are slightly heavier compared to that of protons. Okay, so neutron already has a mass of proton inside it, but also it has mass of electrons. Neutrino is very small mass. Previously it was assumed it has 0 mass. Now they have accepted a very small value for neutrino, but which is almost close to 0. Okay, now it was earlier thought that nucleus may contain electrons, but this was ruled out later using argument based on quantum theory. Obviously we are not going to discuss that, but initially it was thought that some electrons may be present inside the nucleus. Okay, only electron present inside the nucleus is based because of the neutron present. Okay, individual independent electrons do not exist inside the nucleus. Okay, independent electrons do not stay inside the nucleus because of obviously quantum theory reason. But if a neutron comes out of the nucleus and decays, then you might find some electron, because this is coming from the neutron, not from the nucleus. Okay, now the composition of nucleus can now be described by using following symbols. These symbols are very important. First of all, Z is the atomic number. Okay, atomic number is number of protons, atomic number. So if I say an atom, okay, that atom is basically characterizes by this atomic number. Okay, if the atomic number is constant, that means it is the same element. Okay, that is why every individual element has different atomic numbers. Okay, so this is the characteristics of single element. Element of one material will have same atomic number no matter where you dig it up, from India, from Earth, from moon, or from anywhere else in the universe. Okay, atomic number will remain same, but the number that may vary is the neutron number. Okay, number of neutrons. Okay, number of neutrons can change from place to place and it will have a different value. Now the total mass of the nucleus of the element is given by mass number, and it is given by Z plus N. So main important is Z and A. N we hardly use the symbol N, okay, but you should remember this is also something important, but Z and A you have to remember, okay, and the symbol of a nucleus is given by A Z X, okay. So A, suppose mass number is A, it will be come at the top, okay, and if atomic number is Z, it will come at the bottom, okay. Sometimes in some books they write like this also, this is also fine, okay, but now modern most books they write it like this, AZ, easy to write. So this is the symbol that you need to remember, okay. A is the mass number, that is Z plus N, and this is obviously number of protons, okay. Now example is this is gold, Au, okay. Gold has 79 protons and total mass is 197. Now can you tell me what is the total number of protons in this? So total number of proton is 197 minus 79, okay. So it will be 8, 118 is the number of protons inside this, right. So you can calculate that. So if this is given, you can calculate number of protons, number of neutrons, also number of electrons. Why? Because number of electron is nothing but number of protons inside it, unless it is charged. If it is charged, if you say okay plus 2 or minus 2, then you have to reduce that, okay, based on the electrons that is already removed or added, okay. Now size of the nucleus. So it is very important, how big is the nucleus. I gave you one example. If you consider the entire atom to be as big as the classroom, then nucleus is the tip of the pen, right. Nucleus is only of the size of the tip of the pen. Now but that is an analytical example. Now we have to go to exact value. The distance of closest approach to a gold nucleus of an alpha particle, okay, of kinetic energy 5.5 mega electron volt is about 4.0 times 10 to the power of minus 14 meter. We have already learned that in Rutherford scattering experiment. So that means the force the size of the actual nucleus has to be less than this value. So this is the closest distance that a alpha particle can go, okay. So it is not even touching the nucleus, it is going close and then it is getting repelled, right. So it is getting repelled means this is the closest distance that it can reach towards the gold nucleus, gold atom, right. That means the size of the atom should be much smaller than that, because if it was going go inside the atom, that is not possible, right, because it will be repelled because of the Coulomb's force. So now we can say that the size of the atom is much smaller than this 10 to the power of minus 14 meter, okay. In fact, you will see that the radius of a nucleus is given by this, r is equal to r naught a to the power of 1 by 3. What is A? A is mass number. So bigger the mass number, obviously they have lot of number of family members. So mass number more means more number of protons, more number of neutrons present in the nucleus. That means the family is big family. So big family means they will require obviously big space to stay in. So big space to stay in, and it is only a to the power 1/3. R naught is a constant, and R naught's value is 1.2 times 10 to the power of minus 15 meter, or 1.2 femtometer, 1.2 Fermi. Okay, 1 Fermi is 10 to the power of minus 15 meters. Now can you tell me what this R naught represents? What is the representation of R naught? What is the meaning of this R naught? Okay, if you can answer that, mention in the comment below. Okay, we can discuss that in the comment below, even though it is not very relevant, but you can answer that question. This is a very interesting thing. Now, a nucleus at rest splits into two nuclear parts having radii in the ratio of 1:2. Their velocities are in the ratio. Very interesting question. This is also from your previous year question. Very intelligent question. Okay, not difficult but very intelligent question. So nucleus of at rest of a particle, they splits into two halves. Okay, so nucleus splits into two halves and they have radii in the ratio of 1:2. So what is the meaning of radius? Suppose first one is r1 and we know that it is equals to r naught. Suppose the mass number is a. Okay, mass number is a and a1 for r1, and we know that this is equals to a1 to the power 1/3, right? For r2, second part, it will be a2 to the power 1/3, right? Both will have the same formula, but only thing is mass number will be different. So based on that, they will have different radius. Now it is mentioned that the ratio is 1:2, right? So r1 by r2 equals to 1:2, 1/2, right? Ratio means fraction. Now let us put these values. R naught a1 to the power 1/3 equals to divided by r naught a2 to the power 1/3 equals to 1/2. So these are cancelled. These are cancelled means now a1 by a2 whole to the power 1/3 equals to half. Now if you cube both sides, then 1/3 will be gone. So you will get a1 by a2 equals to 1/8, right? So a1 by a2 is 1/8. Now we have calculated the ratio of their mass numbers. Now if we calculate the ratio of their mass numbers, what else we can say? We can say that the mass numbers are of the ratio is 1:8, right? So mass number of the ratio of 1:8, that means mass, actual mass should also be in the ratio of 1/8, because mass number is directly related to the mass, right? Because it is consisting of protons and neutrons. Protons and neutrons are almost equal mass, right? So total mass, if you multiply it with 1 u, then you will get the mass, right? So mass will also be in the ratio of 1:8. Now when a nucleus splits into two halves, so for example a bomb burst into 3 pieces or bomb burst into 2 pieces, then what is conserved in this case? Only one thing is conserved, that is the total momentum of the system, linear momentum. If you remember, you have solved similar questions in your PU1, but up to this part was nuclear physics. After that it is first PU, conservation of momentum. So if the initial momentum of total, initially it was at rest, so initial momentum was 0. Initial momentum was 0. Final momentum is m1 v1 plus m2 v2. Okay, it will come negative. Don't worry about the negative sign. They have asked you the only the ratio. Sign is not important. So m1 v1 equals to minus m2 v2. Okay, or v1 by v2 equals to minus m2 by m1. Right? If you ignore the negative sign, then you know that m1 by m2 is 1/8. So m2 by m1 will be 8/1. So the ratio of their velocities v1 is to v2 will be equals to 8:1. Okay, so 8:1 will be the ratio of their velocities. Is this question interesting or not? Tell me, right, in the comment below. Let me know. This is a very interesting question. It is from your previous year question. One of the previous year, I think 2020, this question came, and I found this question very interesting. Now let's move on. Mass and energy relation. So mass and energy relation, we already learned about this from our previous classes, previous knowledge, from general science, general knowledge book. Okay, what is that? We know that Einstein's famous equation E equals mc square, right? So famous equation, I am not going to discuss much about it. So what is the meaning of this? Meaning of this is, if you take say m mass, okay, if you take m mass, m kg of mass, and if you somehow able to destroy entire m kilogram of mass, okay, during some method, using some method, if you can destroy the m kg of mass, then it will produce energy. Okay, this will produce energy, and how much energy it will produce? The energy it will produce is m times c square. What is c? C is nothing but speed of light. So here the energy equivalent of mass m is related by the above equations, and c is the velocity of light in vacuum and approximately equal to 3 times 10 to the power of 8 meter per second. Okay, so this is a very large number, as you can see. So if you somehow able to destroy 1 kg of mass, if you somehow able to destroy 1 kg of mass, that can be sufficient for to run our country for maybe 10 years. Okay, this will be a huge amount of energy, huge amount of energy. You cannot even imagine. Okay, you cannot even destroy 1 gram of mass. We can destroy some 1 microgram of mass in our nuclear reactors, and that energy is being used. We will discuss about that also in our next part 2, nuclear reactors, etc. But we can destroy only micrograms. Okay, so that mass is huge. Not even micrograms, is much less than that. Okay, in the order of atomic mass unit, that much only we can destroy, and that is going to give us a huge megawatts of energy, and that is giving us the power. Okay, so if you can destroy 1 kg of mass, maybe India can run for almost 10 years. Okay, entire full country with power, full 10 years it can run without any disturbance, so maybe more than that. Okay, I'm just giving you a comparative figure. Okay. Now, so you can imagine that mass is a huge tool. It has a very huge potential to be converted into energy, because we know that at the beginning of the universe, okay, when there was nothing, okay, energy was only thing that existed. From energy, through Big Bang, mass was created. So mass was created from energy. Okay, and that somehow, if you can destroy that mass, eventually it will go back to energy form again. And it was Einstein who first figured this out, and he said that mass and energy are nothing different, they are related. You can destroy mass and you can get energy. You can combine energy and you can create mass. Okay, that is also possible in some way. Okay, so mass and energy are convertible. Okay, so equivalent mass, that's why it's called equivalent energy or equivalent mass. This is a theoretical equation. This exact equation is theoretical equation. There are some practical applications as well. We will see that in a while. So that is called nuclear binding energy. The practical application of mass energy relation is nuclear binding energy. We have seen that the nucleus is made up of neutrons and protons, right? So for example, you consider a bucket. Okay, a bucket is there. In that bucket has no mass. Bucket is paper bucket, it has no mass. You put 10 apples and you put 10 oranges. Okay, what will be the total mass of the bucket? Each apple, suppose you have a bucket, okay, and in that bucket you put 1 apple. Each apple has a mass of say 200 grams. Okay, each apple has mass 200 grams, and you added 10 such apples, 10 apples, and you have oranges which weighs say 150 grams. Okay, and you added 10 oranges as well. So this is apple, this is orange, 10 oranges as well. What will be the total mass of the bucket? What can you expect? What is your expectation? You can expect that, okay, there are 10 apples. 10 apples means 200 grams times 10, that is 2000 grams, that is 2 kilograms. And there are 10 oranges, each of 150 grams. So there will be 1.5 kilograms. So total mass you are expecting, if you weigh in a machine, you are expecting that mass of this will be 3.5 kilograms, right? So similarly, if you consider a nucleus, nucleus consists of proton and neutron. So when you measure the mass of a nucleus, what are you expecting? You are expecting that total mass of the nucleus should be equals to total mass of the proton plus total mass of the neutron, right? That's what we can expect. but in reality it was found that the total mass, the nuclear mass of M found to be always less than this value. Okay, so we are expecting that the mass of the nucleus is equal to the total mass of the neutron and total mass of the proton, right? But when it was measured, it was found that the mass of the nucleus, even though it has 10, suppose, so for example, in this example, you have 3.5 kilograms should have been the mass, right? But when you measured it using a machine, you found that it has only 3 kilograms of mass. So where did the 500 gram goes? So if you consider this in an atomic scale, instead of apple, each apple representing a proton and each orange representing a neutron, you measure their masses, you added them, you expected, okay, if I put this in the machine, I will get the mass equals to the total mass. But instead what you are getting is less than that. So you are thinking, okay, that seller guy must have cheated. So in this case, God must be cheated on us, right? Even though they have given higher masses, but actually the atom weighs less, the nucleus weighs less. So why it is so? Because that difference in energy is stored. Okay, difference in energy is stored. We will discuss that, and that difference in energy is called mass defect. Okay, that difference is called mass defect. Okay, and mass defect formula is given by delta M equals to Z is the number of protons times mass of the protons plus A minus Z. A minus Z is the mass of neutron, number of neutron times Mn, that is mass of neutron. This should have been the mass. So this is the actual 3.5 kilograms. And this is the actual measured mass of the nucleus. So this is 3 kilograms. This difference is called mass defect. So this is the defect that is there in the nucleus from the beginning. Okay. Now what is happening to this defect? It is if you want to break the nucleus into its constituent protons and neutrons. So suppose I took one atom or nucleus, I took one nucleus and I am trying to break it using some method, okay, using hammer or some sophisticated method. Hammer is just an example. If you want to break it, okay, I want all the neutrons, all the protons separated from the nucleus. Nucleus should not be there. So what you have to do, you have to provide this much energy to the nucleus to break it apart. Okay, to break apart a nucleus, the amount of energy you have to give is actually given by delta mc square. Okay, so delta mc square is the extra energy that you have to supply to break the nucleus into its constituent particles. Okay, so if you want to break the nucleus into its constituent particles, neutrons and protons, extra energy delta mc square must be supplied. So delta m times c square. So this is the equivalent mass, right? This energy required is related to the mass defect by Eb equals to delta mc square. Now this is called binding energy or nuclear binding energy. Eb is called nuclear binding energy. So basically this energy binds the entire nucleus together. Okay, this energy, this is why our nucleus is not breaking apart, it is stable, even though individually proton is stable but neutron is not stable. Also protons and protons, two protons are very close to each other and they are repelling each other using Coulomb force, but still they are not falling apart. This is one of the wonder of nature. Okay, this is one of the wonder of nature. Even though two positively charged particles staying close to each other, okay, they are not repelling each other and the nucleus is not collapsing, not breaking apart because of this binding energy. Binding energy is something which is binding the entire nucleus together, right? Now the binding energy per nucleon, this is also important, binding energy per nucleon is also important, that is binding energy. So if you, so binding energy per nucleon, you can say that you have say 10 chapatis in your home and you have 5 members in your home. So how many chapatis per person in your home, average, how many chapatis per person in your home? So it will be 2 chapatis. How you calculated? Total number of chapatis divided by number of person in your home, right? So 10 divided by 5, that is 2 chapatis. Similarly, total binding energy in the nucleus say has some value, and the nucleus has some certain number of members in it. So based on the how many protons and how many neutrons are there, that is called nucleons. One more important thing, protons and neutrons together are called nucleons. Okay, nucleons means whatever inside the nucleus, that is protons and neutrons. Protons and neutrons together are called nucleons, and average energy per nucleon is given by EBN is equal to total binding energy divided by the mass number, right? So this is the binding energy per nucleon. Let us now solve this binding energy problem. Okay, binding energy per nucleon related problem, very interesting problem. The mass defect of helium-24 is 0.03 U, that is atomic mass unit. The binding energy per nucleon of helium in MeV is. So they have asked you to calculate the binding energy per nucleon for helium nucleus. The mass defect is given 0.03 U. Now this is a problem from your previous year questions, PYQ questions. Now, so mass defect, that is delta M, is given in terms of 0.03 U. Now can you calculate this? How can you calculate the mass defect is given? How can you convert it into energy? First of all, you have to find the binding energy. There is a long process. We can convert it using Einstein's relation, Einstein formula. That will be a very long process, but I will teach you a shortcut method. What is that? You can directly convert if the unit is given in terms of U. Okay, if it is given in terms of atomic mass unit, then you can directly convert it into energy. How? To convert it into energy, you have to multiply the U with a factor 931.5 MeV. This is the meaning. 1 U directly can be converted into energy 931.5 MeV. Okay. Now based on the problem, based on the situation, sometimes we will approximate this as 930 MeV, and sometimes we will approximate even as long as 1000 MeV. Okay, based on the given question, given data, you can approximate it 1000 MeV as well. We will see that. We will approximate in this problem, we will approximate it to be 1000 MeV, and we will solve it, because we are trying to find as close as possible value. We do not need the exact value because the options are given so far apart. If you get the closest value, then you can answer this question easily, right? So our objective in this problem, in any competitive exam, not always to find the exact values, except if you are answering the numerical questions in JEE, there your answer should be as close as correct as possible. Okay, even for one digit mistake, maybe you will lose mark. So other than that, you will always for any multiple choice questions, you can approximate the values as much as possible, and you can calculate the closest possible value, right? So now, what is the equivalent binding energy? Binding energy, total binding energy is this. Now what is the binding energy per nucleon? Binding energy per nucleon is EB by mass number. What is the mass number here? Mass number for helium is 4. So EB by 4. So it will be 0.03 times 931.5 divided by 4. Right. Now as I said, instead of using 931, I will approximate that to be 1000, so that our result is, so I will approximate this to be 1000, right? Now if I approximate this to be 1000, 1000 times 0.03 will become 30. 30 divided by 4. 30 divided by 4 will come out to be 7 4s are 28, 28, then there will be 20, 20 means 5 4s are 20, right? 7.5. So our approximated value is 7.5 MeV. Now you can answer what is the correct answer. Correct answer is obviously 6.9 times 6.9825, okay, because this is the closest number to this value. So correct answer is option B, okay. Neither 2.7, it is not close to 2.7 at all, it is not close to 27.93. obviously these are only given to you, confused to you. If you make any decimal mistakes, you will get wrong answer. So here you can get the value 7.5 MeV is the energy per nucleon for helium nucleus. I hope you enjoyed this question. Now let's move on to the next part. Let us see binding energy per nucleon versus mass number graph. This is very important graph. So binding energy per nucleon, if you plot binding energy per nucleon for different elements and their mass numbers respectively, then you will get a graph like this. Now if you see, initially the binding energy per nucleon is low, as expected. The mass number itself is very low, so binding energy, they do not require much binding energy. Now as you are going higher and higher, you see between these 2 points the graph is almost a straight line, almost flat line. Then if you see, the graph is changing from 45 to almost 200 or 175. So mass number is huge. So for a very huge mass number, the fluctuation in the value of binding energy per nucleon is almost constant, which is a very surprising to see. Now we will see the observation from this graph. What all we can see from this graph? First of all, the binding energy per nucleon EBN is practically constant, that is independent of the atomic number for middle region of the graph. For the middle region of the graph, the binding energy is almost independent of the atomic mass number, okay. Someone having mass number 45 and someone having mass number 175, they almost have the same binding energy, right? So they do not depend on the mass number. Binding energy per nucleon is constant. Total binding energy will be obviously different, but binding energy per nucleon is constant. EBN is lower for both light nuclei and heavy nuclei, right? So for A less than 30 and A greater than 170, for both cases we can see that the graph is growing on one side like this and it is one side like this. So basically it is less compared to middle region when you are going higher atomic energy and you are going lower mass number, okay. So for lower mass number as well as higher mass number, atomic and binding energy per nucleon is less, okay. Now what we can conclude from this graph? So the conclusion that we can make from the graph is the force is attractive and sufficiently strong to produce a binding energy of a few MeV per nucleon. So the force is very strong, right? We have seen that for we have solved one problem from previous year where we have calculated the binding energy to be 75 MeV, right? 75 MeV per nucleon. So binding energy is very, very strong, right? The constancy of the binding energy in the range less than 30 to 170 is a consequence of the fact that the nuclear force is short ranged, right? So nuclear force is short ranged. A very heavy nucleus, say A equals to 240, has a lower binding energy per nucleon compared to that of the nucleus with A is equal to 120. Thus, if a nucleus A equals to 240 breaks into two A equals to 120 nuclei, the nucleus gets more tightly bound. So what is the meaning of that? Because higher mass number, that is mass number of say 240, has less binding energy per nucleon, right? But if, because the less binding energy means it is unstable in nature. So unstable in nature means it will break apart into two more closely packed nucleus, that is 120, okay. So for example, if 240, mass number 240 breaks into two smaller nucleuses, each having mass number 120, okay, they will have the higher binding energy per nucleon. That means they will be more tightly bound, right? Thus A is equal to 240 breaks into two 120 nuclei, nucleons get more tightly bound. So nucleons are more stable now. This implies that energy would be released in the process. This is known as fission. Okay, so when a nucleus, heavy nucleus, which has less binding energy per nucleon, once they break into two more daughter nucleus, they are called daughter nucleus. Okay, daughter nucleus having less mass number, okay, they becomes more stable. That means the extra energy that they had, they will be released. So that in this process is called nuclear fission. Okay, you should know the name nuclear fission. We will discuss about fission and the next one again in our next topic. There we will be discussing in detail. Now consider two very light nuclei A less than 10 joining to form a heavier nucleus. The binding energy per nucleon of the fused heavier nuclei is more than that of the binding energy per nucleon of the lighter nucleus. So again same process is happening. Now we are doing it for the lighter nuclei. So we did the process of heavier nuclei where the heavier nuclei broke into two smaller nucleuses. Here what is happening? Two smaller lighter nuclei, they are combining to form a heavier nuclei. Okay, so this in this case also energy will be released, and this process is known as fusion, nuclear fusion or simple fusion. Fusion is common term. Fusion means when two things mix together, they are called fusion, and this nuclear fusion is responsible for energy production in our sun. We will discuss about fission and fusion, whatever they are in your syllabus. It was reduced obviously in your reduced syllabus, but we will discuss that in our upcoming lecture. Now it is time for homework. Let's solve the homework. Homework number 1, you can pause the video, you can read the question, answer it in the comment below. I will say if it is correct or incorrect. Okay, this is homework number 2. This is also from your previous, both homeworks are from your previous year questions. So I request you to answer these two questions as quickly and as efficiently as possible and mention the answer in the comment below. You can use the table for required to solve this question. For example, to solve this question you need the atomic mass unit of protons and neutrons that you can use from the lecture data notes given from this given in this lecture, and then you can solve it. And also remember that 1 U is equal to 931.5 MeV, approximately 930, and sometimes you can take it as 1000 as well. Right now, entire lecture series is uploading in our only one playlist. You can visit our channel, you can check this playlist and bookmark it so that you can access it anytime from anywhere. Okay, and all the latest videos are there in our current playlist, and every Sunday we are conducting KPL. So for that you have to join our WhatsApp group. The link is given in the description. Don't forget to join our WhatsApp group, and this entire KPL series is for absolutely free of cost, and the lecture is obviously for free. Okay, and I hope this is going to help you, and if you are enjoying this, don't forget to leave a comment in the comment box, and don't forget to share with your friends, subscribe to our channel. Thank you. I will be back with Nuclei part 2 along with remaining PYQs tomorrow. Till then, bye bye.